Hello, calculus. I decided to make a video over the 8 problems that I gave you. Just thought it would be, nice to go over them a little more thoroughly. So let's jump right into it. Um, Number one, I think hates me. I just started making this video and I realized that my answer was wrong again. And I feel like if I put myself on blast here by doing it live on the camera, that I won't mess up. So let me share you my thoughts. I have a hard time visualizing this graph just like right away. I know there's a parabola and I know there's a line, but I guess I'm like, is it like this? Is it like this? I'm having a hard time imagining what's happening. So, I think it's nice to factor the parabola, um, factor the parabola. They got a GCF of 6x. You're left with x minus 3. Why do I factor it? Because now I can see that the zeros are at 0 and 3. So I know my parabola touches the x-axis at 0, 1, 2, and 3. And so the parabola is going down like this. Okay, cool. I already plotted this ahead of time, but I still messed up the answer, right? But that's the realization that you can make. And then this is new, what I'm doing here. Set them equal to figure out when slash where they intersect. Set the parabola and the line equal. So when you do that, you're going to get this. Factor out the 6x. And your two solutions are 0 and 2. So interesting. They're intersecting here at 0 and also at 2. So something like this. There's your line. And then we're also bounded by x equals 1 and x equals 3. And when I plotted this in class, I think I misspoke because it says, what is the total area of the regions between these curves? And I started talking about this. And that is inaccurate. That the x-axis is not one of the given bounds. The region that we're talking about is this and this like bow tie-esque looking thing. So the math that ends up happening here is we want the integral from 1 to 2, this region. Which region is lower, or which function is lower? The parabola initially. So we're trying to find the difference. Let me super zoom in. We're trying to find, this distance, right? Like how far apart are they? And then we'll need this distance. So what I'm doing here is I'm doing parabola minus line. I'm doing parabola minus line from 1 to 2. And then I'm going to add that with the integral from 2 to 3. Now the line is lower, and I'm going to do line minus parabola. So this turns out to be a plus 6x added with the negative 18x is the integral from 1 to 2 of 6x squared minus 12x plus the integral from 2 to 3 of this is going to be plus 18x. So that's going to be a positive 12x. And yeah, so this, let's see what happens here. So this is going to become 3x, no, it's not, 2x cubed minus 6x squared from 1 to 2. Bump it up by 1, divide, you get 2. Bump it up by 1, divide, you get 6. And then this is going to become something similar here, negative 2x cubed plus 6x squared from 2 to 3. And when you do the bounds here, if this doesn't work out, I'm going to cry. And then when you do the bounds here, you do 2 times 2 cubed minus 6 times 2 squared minus, plug in the 1, 2 times 1 cubed minus 6 times 1 squared. Plugged in the 2, boom. Subtract, plug in the 1, boom. And this comes out to be, let's see how much we can do a little bit in our head. 2 cubed is 8 times the 2 is 16 minus 2 squared is 4 times the 6 is 24. So 16 minus 24 is negative 8 minus, this is 1 cubed is 1 times 2 is 2. So 2 minus, this is simply 6. So 2 minus 6 is negative 4. We're subtracting a negative 4. So let's just go ahead and write plus 4. And this comes out to be negative 4. It came out negative, and I had a feeling that that might happen because it's under the x-axis. So really we could just say absolute value, right? Because at the end of the day, we just want the area. So taking the absolute value will make it positive. And then when we do this math is going to be negative 2 times the 3 cubed plus 6 times 3 squared minus, and then plug in the 2, negative 2 times 2 cubed plus 6 times 2 squared. Just plugging in the 3, plugging in the 2. All right, let's see what happens here. This, I have some room, so honestly, I don't need to like do it all in my head. This is going to be 27. This is negative 54 plus, this is what? 3 squared is 9. 9 times 6, that's a positive 54. Interesting. I wonder why that happened. Interesting. Okay, and then this is 2 cubed is 8 times negative 2 is negative 16 plus 2 squared is 4. 4 times 6 is 24. So this is just 0, interestingly enough. And then this is negative 16 plus 24 is 8. So minus 8. So that's negative 8. Again, it came out negative because we're underneath the x-axis. Take the absolute value. That's a positive 8. And 8 plus 4 is 12. And I freaking finally got the right answer. Oh my God. All right. And that only took 8 minutes. All right. So I hope that makes sense, though. A lot of algebra just happened at the end. Well, a lot of like arithmetic, I should say. But in the end, I hope that makes sense. It finally makes sense to me. This, I was not thinking about the bounded region correctly. This is going to be the longest problem. The other ones are a walk in the park in comparison, at least to my brain. I don't know where you're at, but I totally thought we were talking about here. Oh, what a mistake. All right, let's move on. I already have these problems done out with no issues, so I'll just kind of go over my work. What is the area of the region in the first quadrant? That's kind of a nice little detail. First quadrant bounded on the left by the graph of x equals y squared over 2 and bounded on the right by the graph of x equals 3y minus 4. So I don't actually know what these graphs look like super offhand. I mean, I could try to graph them, but they were really helpful by saying left and right. So if I have the y-axis here, I'm going to do the right function minus the left function in order to find the distance between the two. At the end of the day, you're trying to find the difference between the two. So them telling you which one was which just allowed me to very straightforward go, oh, the right function minus the left function with respect to y. And then you just integrate. So this gets bumped up and divides. So that becomes 3 halves y squared. This just becomes a y. And then this gets bumped up to a 3. When you divide by 3, that's going to become a 6th along the bounds from 4 to 2. So really importantly, setting up your integral. I hope that you're not wasting too much time. It's just like, oh, because we're with respect to y, right? You can tilt your head a little bit, right? Here's the y-axis. Here's the function on the right. Here's the function on the left. Do you feel me? Right? If you rotate it. So you do right function minus left function. Anyway, the rest of the math pursues here. This is going to be 4 squared, which is 16, divided by 2 is 8, and 8 times 3 is 24. This is going to be 4 times 4, which is 16, and then this is going to be 4 cubed, which is 64 over 6, and I reduced it to 32 thirds. 64 over 6 is 32 thirds. The 24 minus the 16 is 8, and I kind of left it there for a moment. Then I did the 2 next. So this is 2 squared, which is 4, divided by 2 is 2, and 2 times 3 is 6. Plug in the 2 here, that's simply 8. Plug in the 2 here, 2 cubed is 8 over 6, simplifies to 4 thirds. You're subtracting this quantity, right? So the 6 minus 8 is negative 2. When you subtract the negative 2, oh, that becomes plus 2, and I can add it with the 8. And when I subtract the negative 4 thirds, that becomes positive 4 thirds, and negative 32 thirds plus 4 thirds is negative 28 thirds. Then I looked at the answer choices and was upset because they didn't simplify their fractions. So, minus 56 sixths. Guess that goes to show I should look at the answer choices before starting. All right. Number 3 in class, I also voiced to you that I was a little surprised by this. But when you go back and look at the wording, the base of a solid is the region bounded by the x-axis and the graph of, and that's all they say. So I did not look at this and instantly think a semicircle that is touching the x-axis about -1 and 1. That's what it is, but that's not what I thought. But I'm like thinking to myself, if you're looking at this as a square root and you're like, this has got to look something like this, doesn't it? Like it's got to be a square root. If that's what you're thinking. You're thinking to yourself, well, where does the boundary end? They can't tell you. They can't not tell you that. Okay. So again, it comes down to just simply, if you want to know where things begin and end, you want to set them equal to each other. So when is this given function equal to the x-axis? The x-axis is 0. Okay. So when you set those things equal to each other, turns out they're equal to each other at positive and -1, and voila, you found your bounds. Does it really matter if it's a semicircle? No. It doesn't matter that it's a semicircle. What matters is that you now know your bounds, -1 to 1. Of course, the square root function is the thing that's being squared, right? Like, that's just a given. But it's the bounds that were kind of tricky, I feel like. So to further read the question, for the solid, each cross section perpendicular to the x-axis as a square. So that's why I said it's kind of given that it's squared, because this distance, turns out this graph is not correct, and it turns out the graph looks like this. So the edges of the square are the vertical distance here, which is the function, of course, right? The function, it's function tall. So, yeah. So you square it because that's what you do. Side times side, side squared. And when you square this, that gets rid of the radical, which I just kind of did in my mind. I was like, okay, poof, it's gone. So I just kind of ignored the radical and integrated. So when you integrate the 1, that becomes x. And when you bump this up by 1 to a 3, you divide by 3, and that's why that looks like that. And along the bounds, -1 to 1. You plug in 1, that's just a 1. That becomes 1/3. Fool. Minus, you plug in a -1. Fool. When you do that cubed, it's a -1/3, but the double negative becomes a positive 1/3. So -1 plus 1/3 is negative 2/3. And then, oh, another double negative becoming a positive. So the 2/3 and the 2/3 make 4/3. The answer choice. So I think if there's a lesson learned here from example number 1 and example number 3, it's that if you can't visualize the graph, setting things equal is probably your best bet, because you need to know the bounds. And if they're not going to tell you the bounds, I guess the intersection is the bound, and you're going to have to find that intersection by setting them equal. All right, let's continue. So the base of a solid is the region in the first quadrant. That's a key detail. That's helpful, right? Like, okay, I'm above the x-axis. That's cool. Between the graph of y equals x squared, that's a parabola, easy to visualize, and the x-axis for 0 to 1. For the solid, each cross-section perpendicular to the x-axis is a quarter circle with the corresponding circle's center on the x-axis and one radius in the xy plane. What is the volume of the solid? So, what they're saying is when you draw the parabola and you have these perpendicular things from 0 to 1, that is a quarter of a circle. So instead of the figure like looking like this with a bunch of semicircles that are creating a solid, it's a bunch of quarter circles that are creating a solid. So it's like some sort of a shape like that. Is that beneficial? Can you tell what I'm doing there? Here, let me try again. How would I do this? Can I do this? Right? Just something like that, right? It's like all quarter circle. It's not exactly like that, obviously, because this is a parabola. But the distance from the parabola to the x-axis, that's the radius of the circle. So the radius is the function. And I have pi over 4 because I'm doing a quarter circle, not a semicircle. So the pi over 4 is chilling along the bound 0 to 1 because they said so. And when you do that, when you square, I'm squaring because it's pi r squared. That becomes x to the 4th. And when you integrate, that becomes x to the 5th over 5. And then along the bound 0 to 1, the 0 doesn't matter. So when you plug in 1, 1/5 times pi over 4 is pi over 20. That one's not too bad. What's bad about that is like not being like quarter circle, like just divide by 4, move on. The region R in the first quadrant is enclosed by the lines x equals 0, y equals 5, and the graph of blah blah. The volume of the solid generated when R is revolved around the y-axis is... So revolving around the y-axis means we need it in terms of y, which is what I've accomplished right here. So I subtracted the 1 and then took the square root, and you've got, technically it's plus or minus, I suppose, but plus or minus the square root of y minus 1 equals x. This is the positive half. And yeah, so the bounds are from, if you're not sure how I got, I mean, hopefully 5 is obvious because they told us y equals 5. But if you're unsure of how 1 occurred, it's because we were told the equation of the parabola like so, which means the vertex is at 0, 1. That's what this vertical shift up 1 is telling us. So we know that this is touching the y-axis at 1. And then because this is the line y equals 5, we know that that's the top of the region. So from 1 to 5. And then my shading is kind of crappy, but really we're thinking with respect to y. So we're thinking like this direction, right? So what is that distance? That's the function. So function with respect to y, or in terms of y. So I wrote it as y minus 1 to the 1/2, so it was a little clearer how the square and the 1/2 cancel out. you're left with y minus 1 dy. Don't forget the pi. This is squared, right? It looks like I forgot the pi right here, but it's pi r squared, right? This is the radius of, and this is going to get rotated around. So we're calculating the radius of this circle that's about to be generated, these disks, right? And we've got this. So when you integrate that, just bump that up by 1 and divide. That's why that. And then that becomes minus y from 1 to 5. When you plug in the 5, you get... wait. Am I missing some work here? Yeah, I feel like I'm missing some work here. Let me backtrack. Is there the point is it comes out to 16 over 2, which is 8, and then times the pi. I'm not seeing all my... Oh, I did a lot in my head here. That's what I did. So this was 25 over 2 minus 10 over 2, because you're plugging in 5. 25 minus 10 was 15 over 2. Yeah. So I can, here, let me write that work in so that way, because if I couldn't see it, you probably can't see it. So this was becoming 25 over 2 minus 5, which I rewrote as 10 over 2. And that's where the 15 halves comes from. And then 1 half, negative 1 half, sorry, is coming from, you're plugging in the 1. So 1 over 2 minus 1, which is negative 1 half. When you subtract minus the negative half, that's plus a half. So 15 plus a half is 16. 16 divided by 2, 8. Times the pi, right? This is all, I'm getting lazy, right, with my times pi, but this is all times pi. All times pi. And on a free response question, that matters, right? And, you know, I should be more diligent, but, you know, we've all been there. All right. The region in the first quadrant bounded by the graph of y equals blah, secant of x equals pi over 4, and the axis is rotated about the x-axis. What is the volume? So, if you don't know what the graph of secant looks like, that's fine. Doesn't really matter. All you need to know is that, like, nothing. You don't need to know anything, right? You just need to go from 0 to freaking pi over 4, to be honest, right? The fact that it says and the axis, right? That is saying bounded by the y and the x, right? The plural of axes is axes. Let me double check that. Plural of axes is axes, A-X-E-S, which is hysterical. So, and the axis. So the secant function looks, I don't know, like something like this or something. And it's, so what we're saying is it's bounded by this axis, and the line pi over 4. Anyway, that's all to say that the x equals 0 line is the y-axis. So that's why this is 0. And then the x equals pi over 4 is the top bound. And then we're squaring because this is the radius, right? If you don't know what the secant function looks like, that's fine. But the point is that the radius is the function. The radius is the function. You don't have to overthink it. The radius is the function. The only time the radius isn't just the function is when you're rotating around a line other than an axis. But if you're rotating around an axis, you don't have to think that hard. So pi r squared, the integral from 0 to pi over 4. The integral of secant squared is tangent. When you plug in the bounds, tangent of pi over 4 minus tangent of 0. Tangent of pi over 4 is 1. Tangent of 0 is 0. 1 minus 0 is 1. And 1 times pi is pi. 2 more. What is the volume of the solid generated when the region bounded by the graph of y equals 4x? I just went, drew a line super quickly. The horizontal line y equals 8, I just drew a line super quickly. And the y-axis is revolved around the horizontal line y equals 8. So this triangle is being rotated around, okay? It's being rotated around, so lovely pi r squared. The radius is a little cheeky here because we're not rotating around an axis. So what is the radius? The radius is this distance. The radius is that distance. So if everything's with respect to x, we're thinking 8 minus this stuff will leave us with this stuff, right? So 8 minus the line. Top function minus bottom function in a nutshell. Top function minus bottom function in a nutshell. So 8 minus 4x is your radius. Square it. When you square it, of course, this happens, right? FOIL, distributing, all that jazz. And integrate. Bump it up by 1. Square it. Divide by 2. Dividing by 2 is 32. Bump it up by 1. Dividing by 3 doesn't simplify. Boo-hoo. So we cry a little bit because we have 16 thirds, but we move on with our life. Don't forget the pi from 0 to 2. And then from 0 to 2, the 0 is not going to matter, thank goodness. So we just focus on the 2. You plug in the 2, 64 times 2. Oh, I'll do it. I wrote it up here. 64 times 2 is 128. Plug in the 2 here. That's 2 squared. So that's going to be 4. 4 times 32 is 128. And someone's calling me. Hold on a sec. All right. And I ended up stepping away, had that whole phone call. I don't even know where I left off. I think it was somewhere in here with the 128s. The point is the answer is 128 pi over 3. I think that's an easy place. That was a good place for me to leave off. So, boom. I don't know where I left off. It's too late now. All right. And the last question, number 8. Let S be the region enclosed by the graphs of y equals 2x and y equals 2x squared. Again, those were like pretty quick to just like graph, so not that too big a deal. What is the volume of the solid generated when S is revolved around the line y equals 3? So again, because we're revolving around a line other than an axis, then we kind of have to, be a little bit concerned. But again, it's just simply top minus bottom. And this is washer method because you've got 2 functions. So top minus outer minus top minus inner, right? So I forgot the pi over here. But our bounds are 0 to 1 because that's where the intersection is occurring. I set the 2 functions equal to each other and found that they were intersecting each other at 0 and 1. So we know that's our bounds. And then, yeah, like I said, the parabola is the outer. So that's 3 minus parabola squared. That's the outer radius, the capital R that I was using in our notes. And then our inner radius is minus the line. And then you just come over here and you see, and this is one of those classic examples where it's just the setup and not actually solving. And 8A. All right, perfect. So, and that's just under 30 minutes. What an incredible video. Thanks for watching. Appreciate your time. Feel free to watch this anytime when studying, and I'll catch you later.